Okay. You don't need explanation for the problem yesterday, no? Yesterday quiz problem, it's okay. You can. I don't need to go through it. Huh? It is just calculation. Okay, if someone wants, latecomer, someone wants, I would. Ah,
It's correct.
Coherence correct.
Yeah.
How is it possible?
No,
You made 2/3. Yeah, but that's okay. Some of the calculation, which calculation you got it wrong? C, you got it wrong. Then it will be difficult. You must have done precisely the same mistake again. Reverse mistake. Yeah. Reverse did some more. Okay, that's okay. Okay, so maybe if somebody latecomer, somebody wants it, we will do it later at the end of the class or some other time. Hmm? Wait, what's happening? Oh, calculus. Who is that? Oh, second. Calculus 2. No, calculus or this is analysis 2 supposed to be. Whatever, doesn't matter. Calculus 2, calculus 1, I think. Yeah, then there are new names, but it's not updated in the website. Okay. So I will want to do many problems, but it's not possible in the class. So I will do one of them. So the one is something like, suppose this is a problem or something. Example. If you have x follows exponential lambda, and y is another variable which follows exponential mu, okay, then we want to calculate what is the probability of x less than y. I mean, of course, they are random variables defined on the same probability space, but they have distribution. We don't know the probability space, but the probability of p of x less than y. So for example, so how do you calculate this? This is so, but this is equal to, I mean, if you want, you can write it like this. Okay, indicator function of x less than y. Okay, this is just expectation of indicator function x less than y, right? Okay. This is, you can write it like that. So then it is just, you have to replace x by small x, y by small y. And then, I mean, we know this formula, no? Expectation of g is integral g with respect to the, I mean, expectation of any g, maybe from Rn or something like that. This is a two variable function. You can write it. So this is just integral over, double integral over the same set, where all those xy such that x is less than or equal to y, okay, on this f of xy dy dx. Is right? The reason is this, you can write it like this. Okay. Then if you use that, we have proved that. Okay. Otherwise, also this is just the set, you can go through set theoretically. It's the same thing. Okay. I mean, it is just this. Okay. You can get convinced in more than one way. So now this is equal to minus infinity to infinity. Okay. And the other one, I mean, if x or y, whatever, whichever you want to take first. So first we take maybe dx dy. Okay. Then this will become minus infinity to y. Okay, x is less than y, so it will be minus infinity to y. Yes, I want to take it like that. Y. Then f of xy dx dy. Okay. So we can get it like this. Now we know what the formula of this. So x and y independent. Okay. I mean, if it's not independent, you can specify you can take any f and do this. For simplicity, we are taking x and y independent. If x and y is independent, we know what is just the product. The joint density function is just the product. So we just have to find this. E power, so lambda e power minus lambda x, then mu e power minus mu x, mu y, dx dy. Could I just do this? You can do it. It's just e power, no? So it is just lambda mu minus infinity to infinity. If you do it, you just have to integrate with respect to x, which is just e power minus lambda x divided by minus lambda divided by minus lambda, but that minus will go with the yeah, it will be just 1 minus e power minus lambda y. Let me write it. This lambda will go away. Is that right? And then e power minus lambda mu. Sorry, mu y. Is that right? This is just e power minus lambda y divided by minus lambda. From minus infinity to, there is no minus infinity, 0 to y, because it's exponential. So it's only x, I mean, x and y greater than 0. It's exponential, no, it should be greater than 0. It's only for positive values. So this is just 0 to this. So at 0, it will become 1. At y, it will become minus lambda y. But because of the minus sign, I interchange the limit and it is this. So now if so this is just, you have to, so now, yeah. Now this is mu into 0 to infinity, e power minus mu y minus e power minus lambda plus mu y, okay, dy, which is just mu into, at 0 it is 1, but that will get, I mean, it is just 1 by mu minus 1 by lambda plus mu, right? It's just lambda plus mu minus mu equal to lambda by lambda plus. Fine. Okay, one problem. Now next, what do we want to do? We want to consider sum of two random variables. This is sum of two random variables. So xy are random variables, has joint distribution, have xy, I mean, it is just a pair, so it has joint distribution f of xy. Then what is it's? I'm not assuming independent now. Okay, I mean, I will assume independent. Then it's just the product of the individual random variables. Okay, they have this. If you want, I can write it. Or I should not write it. Okay. So xy has joint distribution. Then what is the distribution of x plus y, which is a real value distribution? I mean, which is real value. So, x plus y. We want to find the distribution of x plus y. So we want to find the distribution of x plus y. So which is just f of x plus y at some z. Okay, at some z, and this is just probability of x plus y less than or equal to z. Okay, by definition, and that is just the double integral over x plus y less than or equal to z. Here z is fixed in this integral. X and y will be varying. Z is fixed here. X plus y less than or equal to z. Then f of xy dx, which you can write it as minus infinity to infinity. But then if, I mean, one variable, may say the x variable varies from minus infinity to infinity, the y will vary, but minus infinity to z minus x, right? F of xy dx, first y is dy dx. I mean, you can interchange x and y, doesn't matter. Okay. From this condition, I get this. Okay, one will vary between this. This is this. Okay. Now we just change the variable, which is just minus infinity to infinity, minus infinity. Instead of z minus x, I want to put z prime or something. I want to put x, y prime, or I can put y itself, but a little bit confusing. Z is already there, so I call it u. Okay, u. Okay. U. Then this will become f of x u minus x, right? This will be u minus x, right? u minus x. If it is u minus x, that will become u, right? Yeah. Instead of y, I'm using u minus x. U is equal to y plus x, so this becomes u. Huh? This is okay. Huh? Instead of y, I'm substituting y is equal to u minus x. U is I'm substituting. Then the huh? What? Z minus x. Oh, sorry. Yeah, sorry, Z. Sorry. Is that what your confusion is? Sorry. Yeah, I'm sorry. That is Z. Z is here. Z is a constant in this. I mean, in this integral, there is no, the Z is a limit. I mean, it's a constant. Z is a function variable, but it's a variable outside this. Okay. In this integral, Z is a constant. This is up to 0 to Z. U is the variable, but this is u minus x. Du dx. U is, I'm just substituting. What is u mean? Substitute u equal to y minus x. You can't substitute in an integral, no? Eh? Say it again. No, Z is a constant. Here this integral y is a variable. For this integral x is a variable. For this integral instead of y, I'm putting u minus x. I earlier put u here, which is wrong. But it is z minus x will become z. Okay. Okay. If I substitute this, yeah, it is confusing. Yes, there are too many variables, but this is correct. What I have written. Okay, you just take it. Now interchange the integral. But notice that there is no problem with this integral. This is minus infinity to infinity. This is minus infinity to z. This is just a infinite square. Okay, this is not something like a rectangle where you have to worry about the variable changing. So this just basically becoming infinity z minus infinity to infinity. Z is fixed. Okay, it is just this. Now f of x u minus x. Then you have dx here and then du here. So this says this is minus infinity to z. Here f of z. This is the distribution function. F of z equal to this. These things imply the distribution of x plus y is integral minus infinity to infinity. It's a function of u dx. It's a function of u. I mean, it's a function of, sorry. Yeah, this is a function of u, right? Okay. It's integrated with respect to x, and it is just, okay. Yeah, it is a function of u. And the way in the, I mean, you are integrating with respect to the variable x. Okay. So if independent, if x and y are independent, huh? Here. No, z is outside. U is the one which is varying. And here there was y here. I am substituting y equal to u minus x. Here, f of u, fx plus by u is this. This is the density function. If you integrate it from minus infinity to z, you will get the distribution f of z. Okay. If x has density f and y has density g, then and xy independent, then of course the joint density is just the product of that, of course, with the different variable. Then fx plus y at instead of use is it maybe u is equal to integral minus infinity to infinity f of x g of u minus x dx, okay, dx. Okay. This is actually equal to minus infinity to infinity, f of g of x, g of y, maybe if you want, f of u minus y dy. You can verify by change of variable or something, but still by our calculation, this is to it. This will depend on which way you take. This product is what is called convolution product. This product, this is the product, f star g equal to this. This what is called convolution product. If you have two functions, actually, if you have two integrable function, you can do this. Of course, density functions are integral. Integral is 1. So this makes sense. So if I mean the density of x plus y, where x and y are x and y are independent, is just the convolution product of that. Okay? It is just the product. Okay. What is next? So let us come see an example. Usually, this convolution product will be maybe difficult to compute. Sometimes it's easy, sometimes it's difficult. We will employ other methods like generating function or characteristic function to find the density of the sum. Okay, there it will be easy. So, for example, to compute for normal, it will be difficult, but it will be easy when we go through characteristic function. Okay? We compute the convolution product or the density of x plus y, where x, suppose x follows normal, y follows normal with some mu sigma, some mu sigma prime. Then the sum x plus y will follow mu plus mu prime, sigma plus sigma prime. I mean, the variance will add, the mean will add, but the convolution product will be difficult to, I mean, it's a computation one can do, but it's easier when you look at the characteristic function. Okay, so this we have seen already, the probability generating function. Sometimes it's easier to find the mass function of the sum, discrete variable. Mass function of the sum is just the product of the generating function. I mean, generating function of the sum of independent thing is just the product of generating function. So it's easier to handle that. Okay? So, but this example is simple, so we will just do that. Suppose, yeah, this is something interesting. Suppose x, y, both follows. I mean, then it comes easier. So that's why both follows exponential lambda. Otherwise, also you can compute it, but this gives a nice answer. Okay. Then what is the x plus y? We want to find fx plus y, okay, which is equal to minus infinity to infinity. Okay, f of x is lambda e power minus lambda x. Okay, and that x minus u is just lambda e power lambda u minus x dx, right? By the convolution product. This is equal to fx star fy, which is equal to this. Okay. Okay. The x plus y, I'm just writing the convolution product. This definition, I'm just writing. So I get this. Okay. Now this is equal to lambda square, okay, minus infinity to infinity. So lambda x, this will go. So you just, yeah, but then this is positive, right? So it's 0 to infinity. It is 0 to infinity. But then this cannot be 0 to infinity, x has to be smaller than u, right? So it should be just up to u. I mean, it is 0 after that. Exponential is for negative values, it's 0. Okay. U minus x, it will be, I mean, it's not, it's 0, right? Exponential is lambda e power minus lambda x for x greater than 0. Is 0 if x is less than 0. Okay. So it is just, the integral is between 0 to u. Okay, and we have integral between 0 to u, and it is just lambda u here, dx. But there is no x here, so it is just lambda x e power minus lambda u. Then this is just, how much is this? This is just u. Something is missing here. I think it's correct, right? in 0 to lambda, then lambda e power minus lambda u, lambda that is plus lambda x will go away. It is just lambda u. I have lambda u here. It is 0 to u. Where is minus? This is just a constant here. There is no x here. This is a constant. This is only depending on e. So e power lambda u, I am just taking it out. If you look at it, the same thing happened for geometric distribution. This is just a continuous analog of geometric distribution. Same thing when you compute convolution for the geometric one, it is something looks very similar to that. I think I haven't made a mistake. So it is just this. Okay. Anyway, you can. So it's here. It's easy to compute the convolution function, but in general, it may be difficult. So for that, we want to define what is called characteristic. Okay. So to define characteristic function, we have to integrate complex valued function. Okay. So complex valued function. So we have to consider complex random variable. So what happens is the following: if you have a x which is from omega to complex valued function, okay, such that real part of it is just real part of x and imaginary part of x. Of course, you can define function. If you have a function, complex valued function, just take the real part, you will get a function, real valued function. Take the imaginary part, you will get another real valued function. They are random variables. That's all. Okay, this is a complex random variable. But then complex has more structure, no? You can multiply and other thing. You have De Moivre's theorem, you have many things. You will not have all those things in R2. Okay? You can multiply, right? So which you don't do it in R2. Okay. So if you want to do it, you have to identify R2 with C. So better directly identify. Okay. Okay. So it's a complex multiplication. Okay. I square equal to -1, which is the great invention. Okay. So if you have a complex random variable, means the real part, the imaginary part are random variable by our definition, whatever our definition. The definition is that less than or equal to x, that should be in the sigma. Omega is the sample space. X from omega to complex number is a complex random variable if these two are. Okay, I wrote it first and then wrote it. X from omega to c is a complex random variable if real part of x, imaginary part of x are real random variable. Okay, or real random variable, you just call it random variable. Okay. Okay, that's all. So then we can integrate ex, x be a complex random variable, x is from omega to c. Then we can, ex can be defined as ex real part of x plus I e imaginary part of imaginary. Okay. Or if x is x1 plus I x2, then e of x1 plus I e of x2 if you want. Okay. So it is just you take the real part and you take the imaginary part and just take the expectation. Okay. Everything works. I mean, of course, it has to exist. It has to be less than infinity. All that. I'm not writing all that. Okay. So you just consider separately the real part and imaginary part and do all that. That's all. Okay. So we have one inequality which we haven't recorded, but it's clear. If x is a random variable, x is a real random variable, x is from omega to r, then mod of ex is less than or equal to e of mod x. That's clear because e of this is equal to e of mod of ex plus minus e of ex minus. Okay, and that is of course less than or equal to ex plus e of x. Huh? Right? But this is not. That's right. You can write it as integral, but in general, if you, yeah, okay. This is just the mod, and integral is linear and all those things. So because of this is true. And so from this, I want to prove. Okay, I will come to complex random variable. If x is less than or equal to y, x and y are real random variables. Now I have to say this. If I say just a random variable, it is real random variable. A complex random variable means I will mention it. Okay. So if x is less than y, then ex is less than ey. Okay. That is clear because if x is greater than or equal to 0, then ex is greater than or equal to 0. It is just for discrete, we have already proved. For continuous, it is just We're going to integrate over the thing, that's clear. So because then of course if x is greater than y, y minus x is less than y minus x is greater than or equal to 0. So in the E is linear, we have proved, and from all those things it will follow. Okay, this is what you are. Okay, this is clear. Okay, so if x is less than y, Ex is less, the inequality is preserved. Yeah, what is the question? That is just the minimum of 0, maximum of 0, and x is anything which will will look like that. Positive part minus negative part. Yeah. What are we writing? I want to prove this so that I use that. Complex I am going to prove. First real itself we haven't proved. So that's why at least we haven't recorded. So I am recording it. Okay? For real I am recording it. So this is also for real. Okay. We have done this. So if there is any other inequality, you will do that. So now if x is from omega to complex, okay, then mod of Ex is less than or equal to E of mod x. Okay, this we have to prove. There is a, you can try harder way, but there is a nice trick. Okay? You will not find it in the book. Okay, what I do is the following. You know, any complex number, Z looks like this, e power I theta or e power I theta times mod of it. Okay. So of course, mod of Z is equal to e power minus I theta Z. Okay. So I write it like this: E of x, mod E of x is equal to sum e power minus I theta, sum e power minus I theta, okay, times E of x. Okay, this is right. But then this is a positive number. Even though this looks complex, this is real. Okay, so it is actually real part of e power I theta E of x. I mean, since it is just real. Okay. Now, which one was this was a assigned, but that was for discrete random variable. We are only continuous, considering continuous random variable only now. Okay. Now this is true. Okay. Now expectation is defined through real part and like imaginary part explicit. Another two things I forgot to say. Maybe we should remember that. Maybe I will write it here. So the thing is, expectation for x is linear. I mean, x is complex random variable. X, y, complex random variable, and alpha in C. Then E of alpha x plus y is equal to alpha Ex plus Ey. Let me not do that. You can write alpha equal to alpha 1 plus I alpha 2 and x1 plus ix2, y1 plus iy2. I mean, it is the expectation is defined like linearity, right? You can take the I out. That's what it says. Okay, but then you can inside then it will respect the multiplication. You just multiply everything like complex way. It will be just a bit not messy. It will look a calculation is needed. Okay, and it's clear. Okay, so you can take a complex number inside an expectation. All I want to do is that only. Okay, so now this is equal to this real part. So this. So now this is same as real part of. Okay, you can take this EIT out inside, e power minus IT x inside first. Because I'm saying these two are same. So the real part should be same. Okay. Now this is also equal to expectation respects the real part. That is how it is defined. Okay. So real part of e power minus I theta times x. Okay. Now real part of anything is less than or equal to mod z. Right? So expectation respects the inequality. So this is less than or equal to E of mod of e power minus I theta x. Okay. But then this is mod 1. So this is just equal to E of mod x. Suddenly it gets vanished from that. Okay. You can evaluate expectation. I mean, you take modulus is modulus of a plus ib is a square root of a square plus b square. You can use that to get this, but this is the easiest way to do this. Okay, so we have defined this, and notice that the fundamental theorem of calculus. See, this is notice that this is, I mean, these are functions from some omega to complex valued function we are considering. The functions are not dependent on complex number. If the function is dependent on complex number, then the theory will be different. We are having some omega. I mean, what I am saying is, you can, for example, if you have a f from R to C, okay, then you can differentiate if it is differentiable. You can, so this can be written as f is equal to f1 plus I f2. This real part, imaginary part. If you want to differentiate this, df by dt will be df1 by dt plus I df2 by dt. Here you are differentiating with respect to a real independent variable, not with respect to, I mean, if it is complex number, then the whole theory will be something different. Okay, of course, this definition is same, another thing, but what I'm saying is it is just these things are true. Okay, so this is like differentiating real valued function only, except that it takes only one takes values in the real and another only. Okay, so because of this, and we define the integral also, integral of f dt equal to integral f1 dt plus I integral f2 dt. This is the definition. I mean, with some limits. Okay, integral is also you define like that. So because everything is defined like that, the fundamental theorem of calculus holds. If something is the derivative of that, then you get that. Okay, you get by integrating, you get back that. Okay, provided the conditions hold, it's continuous and all that. Okay, provided the condition. So okay, so in particular, d of e power z by dt equal to e power z by z. Sorry, z. Sorry, I have integrated. Okay, this you can directly compute. There is no, I mean, you don't like, if you don't like it, this is directly you can do it. E power zt. What is e power zt? E power zt. Okay, e power zt is defined to be summation, right? N equal to 0 to infinity zt power n by n factorial. Okay. Yeah. That also will need some calculation. This is easier. This is directly going through that. I'm just e power zt is this. Okay, you have to compute e power zt plus h minus e power zt divided by h, right? Limit h going to 0, right? This is what you want to compute. So you can take out limit e power zt out. Huh? Okay, yeah, right. Correct. Yeah, you can do that. But sign and say, how will you do sign of that? Huh? Sin zt plus I. No. Only I only. E power RT is not cos RT plus I sin RT. It's not true. Okay. Only the imaginary part will differ. Yeah. So you have to worry about both of them, and you have to. Exactly. So whatever you do, you seem to are more comfortable with this. So this is true. Okay. So similarly, if you integrate it, if you integrate e power z t, okay, I mean whatever the limit is, of course the limit is real valued only because it's only t, okay, which is equal to e power z t by z between the limit, okay, whatever you know this. So why we do all these things? That's because this is the definition. Let x be a random variable, then define a characteristic function. Once I should write characteristic. The spelling right? I'm not sure. Okay, characteristic function phi x at t. Okay, for t, any t in R equal to expectation of e I t x. Okay. This is for any random variable. For of course, discrete. I mean, let's write this for both discrete and continuous. We haven't defined for discrete. So for both discrete and this is the definition. Okay. And this is equal to integral minus infinity to infinity e power I t x f of t f of x dx if x is continuous. Okay. If x is continuous, then this is true, e power I t x, right? And which is cos tx plus I sin tx, which you can integrate separately.
Like, why do we define
Because it has application. It's an this is what is called Fourier series, which is some 200, 300 years old, and it has a lot of application. You can handle many things easily by computing the Fourier, converting one function to another function. Okay, your digital, all this digital works from that, right? All your digital, anything digital is it converts to, you have something over a function which is difficult to, then you have a series, and then of course for a big n, I mean you don't, if you have a digital camera, how many pixels, that's what you worry about, okay, right? I mean you don't, it's not really, if you zoom it too much you will not see the picture anymore. However, I mean you zoom it enough so that you will not be seeing anything, right? It's not continuous, it's digital, okay. So it's very, how the amount of preciseness is given by the, I mean, if you have a function defined on an interval AB, you will get a function defined on n corresponding to that Fourier transform. Okay, here it's the other way. If you have a discrete mass function, then you have a continuous function for that. We will come to that. I will come to that. Okay. So this is what is called Fourier transform. Okay. Now instead of considering that function, which is your analog case, you can consider this. Okay. Anyway. Huh?
also useful for solving?
Exactly, many things. Yeah. I mean, in quantum mechanics, the uncertainty principle is defined through Fourier transform. Uncertainty principle, if you measure one of them, the position and momentum, or one is Fourier transform, that's not this Fourier series, that's a Fourier transform. So they are just, one is the Fourier transform of other. So if you measure, if you can measure one of them, then you can't measure the other one. That variance will blow up. So if it is near zero, that will be near infinity kind of thing. Okay. So it's a very highly useful thing. First of all, we have to verify that this is well defined, right? Number one. Yeah. Of course, Pt of x equal to e of e power I t x. This has mod of e power I t x is 1, of course. Huh? Phi x of P x of t, okay, mod of this, okay, equal to e of mod of e power I t x, okay, is less than or equal to, we have proved it for complex number, which is e power I t x. For any random variable, this is equal to 1. Okay. Okay. So because all this e power I t x is 1. No, we have to show that this, I mean, we have to either mass function or density function, this has to exist, or this is less than, I mean, this is, I mean, how do you get this? This is because if you call continuous one, this is just minus infinity to infinity, just f of x dx, right? That will go away. E power itx will be there. Mod of e power itx will be there. That will go away. So this is equal to 1. Or this is equal to 1, and then expectation of 1 is 1. No, I'm just saying you can directly write it like this. This is equal to 1. So expectation of the constant and the variable 1 is 1. That is one way of finding it. Or you want to look at this integral. This is just mod of this will be 1, and you just integrate it just f of x dx, which is 1. So the value of ext mod of this is 1. So this phi x is a function, is a function from R to this. Huh? Say it again. Huh? Okay. So it is just a I mean, it takes values in the circle. Okay. So let us just compute some of the characteristic functions. That's what we will do now first. Okay. So the computation first, your easiest one is of course uniform. Example. Uniform distribution. So uniform distribution, the f of x is uniform on some interval AB, which is the, so f of x is 1 by b minus, right? So p equal to integral, I mean the integral will be between just a to b minus infinity a to b e power it x and then f of x dx. This is the formula to compute it. But f of x is 1 here. So it is just a to b e power it x. So 1 by b minus a. Okay. 1 by b minus. So e power itx. This is equal to 1 by b minus a e power itx. If you integrate it with respect to x, this is just again e power itx divided by it. So there is an it here. Okay. And I mean, this it will go away. Don't worry, it's in the denominator or something. Okay, I mean, if you write it nicely, it will not matter. It will have a limit at 0. It will have a limit, and okay. So you shouldn't worry what is 0. Okay, this is for the time being. I mean, this will have modulus 1. Okay, so it will have modulus 1, so it will not go up. It will have it's a nice function. It's in fact a continuous function. This is a continuous function. We don't need it, but we may not. No, we will need it when we prove inverse one. I will show you how it is, why it's continuous. But you have to accept something. You can take the limit inside, you have to accept. I'll come to that. It's 1 by b minus a, 1 by it, e power itx, which is e power itb minus e power ita. Okay. You can simplify this using sign something, sign. Okay, let's not do all that. Okay. So if we need it, we will do this later. Okay. So this is for uniform. Huh? That is the density, no? Huh? Oh, here there is no one. Okay. Next example, exponential lambda. Okay. Again, p of x follows exponential lambda. Then p x t equal to 0 to, of course, less than 0 it is 0, 0 to infinity, and lambda e power I x t e power minus lambda x, and there is a lambda, we take it out, and dx. This is equal to lambda integral 0 to infinity e power it. Maybe I put the minus outside. So x minus lambda minus I. Okay, x d lambda by lambda minus it. Okay, lambda is real, so this is lambda minus it. There is a minus sign here. That minus sign will be absorbed here. At infinity, its value is 0. I mean, at 1, at 0, it's 1. At infinity, it's 0. So you'll get a minus sign and that will cancel. At infinity, why is this 0? E power minus lambda, which you can write it as e power minus lambda, e power minus it, e power plus it. Okay. This e power minus lambda goes to 0. This is modulus 1. So the product will go to 0. This is, I mean, if you have a bounded sequence, multiply by something going to 0, bounded means above 0, okay, then the product will go to 0. This goes to 0. E power lambda x, e power itx, sorry, as x goes to infinity. At 0, it is 1, there is no problem. At infinity, this goes to 0. This is of modulus 1. So the product should go to 0. What does it mean by saying the modulus should go to 0? Modulus of this is e power minus, it will go to 0. That's all, it goes to 0. Something goes to 0 if and only modulus goes to 0 as a complex number. Yeah. Okay. Okay. Because you are using complex number, we are just trying to be careful. Okay. Okay. Oh, I realize the same thing. Okay. Huh? Final answer is this. That's all. Lambda by lambda minus 80. Which is well defined everywhere for T in R, which is well defined. This is the answer. Now here I am just saying the limit goes to 0, e power minus. Okay, just you don't need it. Okay. Lambda minus 8. Now let's come to the difficult one, which is normal. There are many ways of doing it. You can consider the power series and compute the moments using the power from characteristic function. If the moment exists by differentiating, you can compute as you can expect. See, this is just e power itx exponential of this. Okay. If you expand it, this will be e of summation n equal to 0 to infinity itx power n by n factorial. Okay. So you have x inside. Okay. But then if you can interchange the sum and exponential, okay, which you suppose if you can interchange the sum and expectation linear, but there is a infinite sum. You can interchange because the modulus of that will converge and all that. I'm not using that. I'm not going to do that. This is one way of doing it. For example, while Portstone, that is the proof given. You can look at it. So you can interchange it. Then you will get the expectation here. But as you can see that exn, you get the nth moment somehow by dividing something, differentiating or something. So by differentiating this and evaluating at 0 something, you will get the moments. Okay. So using that, you can actually compute the using something, you can compute using those calculations, you can compute the characteristic function of normal. But here is another way. Use differential equation, very simple differential equation. Okay. Okay. So for normal, first let's follow standard normal, which is normal 0, 1. Okay. Normal 0, 1. That is the density function is just e power minus x squared by 2, 1 by square root of 5. Okay. So now we want to consider the characteristic function Tx of E is equal to integral minus infinity to infinity e power itx 1 by square root of 2 pi, okay, e power minus x square by 2 dx. Just the definition. Okay, definition of the characteristic function, which is equal to 1 by square root of 2 pi integral minus infinity to infinity, okay, cos dx e power minus x square by 2 dx. So you said you know this formula. You know this formula, no? D mu s.
Yeah.
Okay, you know this formula. If you want, you expand it in the power series, and you should know the cos 1 sin 1, and you will get it. Okay, and I times minus infinity to infinity sin tx, okay, e power minus x square by 2 dx. Okay, this is an odd function, right? This is even. Sin of minus tx is same as sin of tx. So the same thing will repeat here. So this integral is 0. This integral is twice the integral between 0 to infinity. Okay. Right? Okay. So the whole thing is just 1 by square root of 2 pi into minus infinity to infinity e power minus x square by 2, or maybe cos I will write first, cos tx e power minus x square by 2 dx. Okay, we just have to evaluate this. So it's okay, no, it is just uniform, no? I will just erase it. I will write it here. Huh? How will you do that? What will you happen? Just imagine what will you do. E power minus x square, but you have no handle. How? Yeah, but only if it is there you can integrate. But cos tx will become sin tx. Sin tx will, it will just, there is an
After that, integrate by parts, so twice again. So it will again become.
let us see whether that happens.
No, it become.
So you just do that. Try that. Yeah, parts will not work is what I think. If you get it, you tell me. Okay. So I just, okay. Now instead, so what we have is the following: txt equal to integral minus infinity to infinity 1 by 2 square. There is a 2. So yeah, 2 times square root of 2 pi. Sorry, there is a 2 which is here. At the 0 to infinity also. I am sorry. Yeah, this is 0 to infinity. Correct. Okay, 0 to infinity. Okay, then cos tx into e power minus x square by 2 dx. Okay. You can differentiate with respect to t. You have to agree that you can take the differentiation inside. That is possible if some condition, if you take the partial derivative, I mean, you can take a limit inside if the whole thing is uniformly bounded by something. Okay. Here this is bounded by 1, this is bounded by 1. I mean, no, this is bounded by 1, there is no t here. This is bounded by 1. There is no t here. Okay. So if you take the whole thing, it's uniformly bounded by some integrable function. This is an integrable function. E power minus x square by 2 is an integrable function. All this cos tx is integrated. So when that is the case, if you have a limit tn, you can take it limit tn inside. To take a derivative sign inside, you have to take the partial derivative. That should be bounded something. If you take the partial derivative, that should going to become sin. I mean, here you are only taking the derivative with respect to t. Yeah, with respect to t. That is because you are hit by this. It is exactly dominated monosis here. So we have these two conditions. One is cos tx e power minus x square by 2 is less than or equal to e power, this mod is less than e power minus x square by 2, which is integrable. And another thing is this derivative with respect to dou of this, okay, dou of the whole thing, which is sine of whatever, sine tx e power minus x square by 2, which is also integrable. Okay, both these things are integrable. So because of that, you can take the, okay, I mean, it is just the both this function and the derivative, both are uniformly bounded in T by some integrable function. Integrable function is integral should be less than infinity. So that's what integrable means, not Riemann integrable. Okay. So because of that, you can take the derivative inside. Okay. So that is equal to 2 by square root of 2. Integration by parts working? Is it not working? Okay. So now you take the integrals inside. This is going to be, if you differentiate cos, it's minus, no? Minus sine Tx, then there is a x outside, right? X outside. Okay, e power minus. Now you can use parts. See, x e power minus. Which you, how do you get? How do you get?
When you take e power x square by 2 constant, you integrate by cos dx, and then you differentiate e power x square by 2. And
You differentiate this and you integrate this.
Yeah.
You differentiate this, e power. You try that. If you get it, you tell me. It will be easier than if you. I'm not sure about it. If you get the, tell me whether you get the final answer. Okay. So this is equal to minus 2. You have this. Then this is I mean this is equal to, it's same as 0 to infinity sine Tx d of e power minus x square by 2. Okay, there is a, yeah. So there is a 2 by square root of 2. That stays as it is. Another 2 where? If you differentiate this, you get e power minus x square by 2, then 2x by 2, which is minus x. You get minus x precisely there. So that's not gone. Okay. So I think this is correct. Okay. D of this, which is just minus x times this. Okay. Okay. Now this is equal to 2 of square root of 2 pi. 2. We have a 2 somewhere. 2 is okay. 2 is fine. So that is equal to 0 to infinity. 2 is needed, of course. That is equal to cos Tx into e power minus x square by parts. Okay. Dx by parts. I mean, we will have another term, but that will be 0 both at infinity. At 0, it is 0 because sine of 0 is 0. At infinity, this is bounded and the e power minus x square by 2 go to 0. Okay. So this goes to 0 as t goes to infinity. Sorry, as x goes to infinity. At infinity, this 0. At 0, this is 0. So there is one, I mean, the other term, there should be a number before this, no? That is 0. And if you differentiate it, you get a sign, you get this. One more t. No, there is no t. 2 root. If you differentiate, no, you are different. If you differentiate sine, no, we have this and once again. We are differentiating, no, there is no t inside. There is t or x. Yeah. Yeah. So what are you saying? You are saying that this will be integrated, so you get e power minus x square. So if you differentiate this, you get cos Tx, then there is a t outside. So why are you saying t square? T, only t. Yeah, that's right. This is fine. Yeah, you have to differentiate that. Yeah. Now there is a two kind of differentiation. Now differentiating with respect to x here. Okay, that is it. That was the confusion. Earlier we differentiation is with respect to t. Now integration by parts, so we are differentiating with respect to x. That's why we got this. Okay, this is correct. But this is just basically, so we have d phi by dt equal to minus 2t into phi of t, right? T. Okay. Which is d phi by phi equal to minus 2 dt, which is just log minus 2t dt. So this is just log phi equal to 2t square by 2, right? Minus t square by 2 I should get. There is a t, 2 should that's 2 should cancel somewhere, no? Eh? What? No, I should get 2. Somewhere the 2, this 2 is here, which should go away somewhere. Minus 2t. Oh, no. This is okay. This is, oh, that is defined through t. The 2 is already here, right? This 2 is already here. So there is no 2. There is no 2. Please just this. Okay, minus t square. Plus some c. I will come to that. This just says that phi of t equal to e power minus t square. By 2. Yeah, by 2. By 2 times some bigger constant. Huh? Minus is coming all the way, everywhere. From where minus is coming? Minus should come. Otherwise, we are differentiating cos, so it should be a minus. Right? Cos tx we are differentiating. So, why did I erase here? Did I erase something?
No, that minus got cancelled by writing it.
Yeah, that minus got cancelled with correct. That is right. So now you are differentiating sine. Sine, if you differentiate, you will not get it. But then, no, it should be minus. Otherwise, it will be a problem. Exactly. There is a minus there. Yeah, it's because of that, right? Integration by parts, something minus that. No. It is just some number minus that. Yeah, it is that minus. Okay, good. Okay. So you agree? Final answer is this. But then phi of 0 has to be 1. E power itx, if you apply t equal to 0, e power itx, that's 1. Phi of 0 equal to 1. So c should be equal to 1. So this implies phi of t equal to e power minus t square by 2. Okay. Up to a constant, we get the same e power minus t square by 2. I mean, that's why I was saying that it should be right. Okay. Huh? Yeah, this is Fourier transform. Characteristic function is just a Fourier transform. Okay. So Fourier transform of e power minus x square by 2 is constant times e power minus t square by 2. The same thing. It's just a constant will go from here to there. Okay. So that's what you got. So we have computed the normal one. Now we want to compute for general normal. Suppose x follows normal 0, 1, then sigma x plus mu will follow normal mu sigma square. Okay, you have noticed this. Okay, now characteristic function of for any AB you can pick. Okay, sigma x plus mu at t for general one I'm saying. Okay, is equal to e power I sigma x plus mu t. Okay, yeah, expectation. This is same as expectation of e power it mu. You can take it out, which is a constant. Then e power I sigma t x. So which is same as e power it mu. We can, this is a constant. We can take constant, complex constant outside expectation, and this is just phi of sigma t. Okay, this is for general. You can have a, b, something, whatever. So now this is equal to e power it mu. You know that e power minus sigma square t square by, if x follows normal mu sigma square, then this is the characteristic function. Okay. See? Okay, why do we do all that? You asked for it. So let's see the application. So for that, I need something which I will prove in the next class. That is characteristic function uniquely determined. If two random variables have the same characteristic function, then they should have the same distribution. Okay. Okay. I mean, they should only have the same distribution. They need not be same. Okay. I mean, it cannot determine the random variable. It only determines the distribution. Okay. So now we want to talk about independence. Okay. If x, y are independent, okay, then a continuous random variable. Okay, we have already seen these things for real, I mean, discrete random variable. Whatever we are going to discuss, we have seen it for discrete random variable, continuous random variable. Then f of x, g of y, so that, I mean, nice function, which are random variables, so that they are random variables. I mean, f and g are such that f of x and g of y are random variables, are also independent. That's okay. Why is it true? Or you don't even worry about it. This is true. E of g of x, f of y is equal to E of g of x times g of f. Okay. I mean, you don't even, this is true. By looking at the distribution or something, it's clear. Okay, but this is what I want to prove. This is also true. This is clear. Okay. But I mean, it is just clear, no? If x and y are independent, then the function of that function of y is also independent, because you just look at the, we know already how this is equal to integral g of x, f of y. This f and g are confusing because I want to use the fx of x, fy of y. Maybe I call it, maybe I use different function, okay, such that h, e, f, h, h and g, h and g, okay, h and g are function, then e of h of x, g of y equal to integral of h of x, g of y, f of x, fy of y, dx dy, right? These are densities of x and y. Okay, right? Double integral over R2, whole of R. So maybe minus infinity, minus infinity. Okay. Now this is just the product, h of x, f of x, g of y, this, they will just join together. This is equal to integral minus infinity to infinity, h of x, fx of x dx, multiplied with integral minus infinity to infinity, g of y, fy of y dy. Okay. So which is same as e of h of x, e of g of y. So any two function, nice function, so that they are random variables, so that g of x and g of, I mean, h of x and g of y are random variables, then this product rule holds for any two things. The converse is also true. That is, we don't need the converse, but I'm just stating it here. Okay, maybe proposition. We proved it for discrete one. So x, y are independent if and only if f of x, g of y are sorry. If and only if e of f of x times g of y is equal to e of f of x times e of g of y. For what kind of function? For all nice function, measurable function, whatever. All function which will make these two things random variable. Okay. But I just write it like that. The discrete you can write any function, but here we cannot write any function. Proof, but we are only going to take one way we have already proved. Okay, proved. Okay. For this way, you just have to take one single function. Okay. Take that to be 1 minus infinity x. equal to G. Huh? No, I'm not taking continuous. Huh? Continuous random variable. Yeah, correct. Because we have proved for discrete random variable, we are proving for continuous random variable. This is true for any random variable, but that proof is different. So for continuous random variable, we are proving this. You take infinity minus x. I mean, this x is fixed. Okay. So this is g of t equal to this. Okay. And similarly, in the minus infinity y t okay, equal to h of t g of t. Okay. Now, if you just apply it, okay, I mean minus infinity x t, you apply it over x. That is just x less than or equal to x, right? E of this, huh? Yeah, for all f comma g. Random variables. Okay. If you want, it's easy. You call it measurable functions. Okay, that's a right notion. Okay, they are called measurable function. But I just take this indicator function. That is enough. Okay, indicator function of this. Okay? Indicator function of minus infinity y. Okay, and this is just equal to probability of. I mean, if you use the integral and another thing, which is the probability of x less than or equal to x, y less than or equal to y. It is just equal to the product. So you just get that. You just get the answer, no? Which is equal to indicator function of. It's okay. Should I write it? Which is equal to expectation of indicator function of minus infinity x times indicator function of minus infinity y, which is just the probability of this less than or equal to this. This is just the probability of y less than or equal to y. So you get, that's what the definition of independence is. So you apply this for this particular function, you get the independence. Okay, this is okay. Okay. This is not part of our course because we don't define measurable function and other things. So yeah, I'm just telling you. Okay. So now what do you want to do? So this is something clear from what we have discussed. Let me just record it. X, Y are independent. Okay. And then phi of x plus y, the characteristic function at t equal to phi of xt times phi of y. This is the product. Proof phi of x plus y t equal to e of e power I t x plus y, okay, which is equal to e of e I t x times e I t y, which is equal to, of course, individual product, which is equal to phi x t. I'm just following one step. Okay, clear. It is just the product, and you get this. So characteristic function of this is this. Okay. Now if x follows normal mu sigma square and y follows mu prime sigma prime square, okay, then and x and y are independent, okay, then phi of x plus y at t equal to phi of x at t, phi of y at t equal to e power I mu t e power minus sigma square t square by 2 e power I mu prime t e power minus sigma square sigma prime square t by 2, which is equal to e of I mu plus mu prime t e power minus sigma square plus sigma prime square by 2. So this implies x plus, this doesn't imply. Once we prove that characteristic function uniquely determines the distribution, if a characteristic function of two random variables are same, then they have the same distribution. If we prove that, okay, then if we prove something, then x plus y follows normal mu plus mu prime sigma square plus yeah it's a what is it variance will add up. Yeah, it is not sigma square. No, the variance is sigma square plus sigma prime square, right? Variance is the square of the standard deviation. The new sigma square is just the sum of that. Okay. Once we prove characteristic function is a 1-1 function, okay, any distribution will have a which is t square. Yeah. Okay. If the characteristic function which is defined on the space of all distribution phi x going to phi x, or I mean some distribution going to phi of that, okay, if that is an injective function, okay, that's enough. Then this will be true. This shows that has the so we have to prove that. It's time, so stop. I'll prove it in the next class. Actually, that proof is not in Poel-Port stone. We will nevertheless prove it.